example 23.12 from page 778 in our textbook. In this problem, we are solving for an object that has a charge Q equal to negative 6.00 times 10 to the negative 9th coulombs. It is placed in a region of uniform electric field and is released from rest at point A. After the charge is moved to point B, 0.500 meters to the right, it has a kinetic energy of 3.00 times 10 to the negative 7th joules. In part A, we are given that if the electric potential at point A is 30.0 volts, we're looking for what the electric potential at point B would be. And then in part B of this problem, we're looking for what the magnitude and direction of the electric field is.
On exercise 23.12. So here are some of the values that the problem gives us to work with. This value won't be used for part A, it's used later on in part B. So in part A, we are looking for the voltage at point B. So we have a particle at point A that is moving to point B. And this problem uses the work energy theorem because we're talking about an electric field doing work to move a charge. So because we're using the work energy theorem for the problem, we can use that equation to help us solve it. So we have work from moving a particle from A to B is equal to the change in kinetic energy of the particle. And we're told that the kinetic energy, that the particle is at rest at point A, so its kinetic energy there is 0. So we can say that KB minus KA is KB minus 0, which just gives us KB. We can also say that the work to move the particle from A to B is equal to negative Q times VB minus VA, where VB is the voltage at point B and VA is the voltage at point A. Now we can rearrange this and make this a little bit more useful to ourselves by just multiplying through by negative 1, which gives us Q equals VA minus VB. Now because these are both set equal to the work done, we can combine these two equations and we can say that KB equals Q times VA minus VB. And rearranging this equation, we'll get VB equals VA minus KB over Q. Now, we're looking for VB in part A, and we have VA, KB, and Q, so we can solve this thing. So the voltage at point B is equal to VA, which is 30.0 volts, minus the kinetic energy at point B, which is 3.00 times 10 to the negative 7th joules, times the the charge, which is negative 6.00 times 10 to the negative 9th coulombs. So, if we work this out, you can plug this into your calculator to verify, we'll get that the voltage at point B is 80.0 volts, keeping the sig figs of 3 significant figures all the way through the problem. So here we have the solution to part A of example 23.12. Alright, so in part B of the problem, we're trying to find the magnitude and direction of the electric field. So we've moved our particle from point A to point B, and we know that the voltage at point A is 30.0 volts. And we found in part A that the voltage at point B is 80.0 volts. So our first task should be to find the direction of the electric field. So we have higher potential here and lower potential here. So it suggests that our field should move from high to low potential, and that our field would be moving towards the left. Now as a check for ourselves, we can also realize that in this electric field, we're moving a negative charge, and negative charges tend to oppose an electric field. So, since we moved our charge from A to B, which is moving towards the right, it makes sense that our electric field would go from B to A and move towards the left. So, now that we've found the direction of our electric field, the next step is to find the magnitude. Now, luckily with this, the problem states that we are operating in a uniform electric field. And because we're operating in a uniform electric field, we can use the equation E equals change in voltage over change in distance. Now, as we were also given the problem, we know that the distance from A to B is 0.500 meters. So, we know the voltage at point A, the voltage at point B, and the change in distance between them, so we can just plug it in. We say we're moving from point B to point A, so the voltage at point B is 80.0 volts, minus the voltage at point A, which is 30.0 volts, over the change in distance, which is 0.500 meters minus 0 meters. This gives us 50.0 volts over 0.500 meters. And when we calculate that out, we get 100 volts per meter. And we got to keep our sig figs. We're using 3 significant figures in this problem, so we're going to put a period right there to make sure we have 3 sig figs for our answer. And as another check, we can see that our units are correct for our electric field. We have volts per meter, which is standard units. So we have our magnitude for our electric field, and our direction being from B to A, or in this problem, left, since it tells us that we moved from A to the right towards B. So we found our magnitude and our direction for part B of the problem, and we've completed example 23.12.